Malay Vanakkam. First of all, I put forth my sincere thanks to our management of Kalasalingam group of institutions for accepting wholeheartedly to conduct this 101 international seminar with the blessing of Almighty and our founder, Chairman Kalvival Devathireti Kalasalingam Ayya. With the support of our chairman, Dr. K. Sridharan sir, I am here to deliver the welcome address for this 101 International Virtual Learning Series in association with the Indian Pharmaceutical Association, South Tamil Nadu local branch, head office at Arun College of Pharmacy. Today we are proud to have an eminent personality, well-known researcher, undisputed researcher, and honorable resource person, scientist Dr. Arun Prakash, the University of Surrey, United Kingdom, to grace this occasion. It is a great pleasure for all of us that he could find time to be with us in spite of his busy schedule. Most welcome you, sir. Your gracious presence is great honor for us and great motivation, inspiration for our entire students. Once again, I welcome you all. Most welcome you, sir. And Dr. Arun Prakash, sir, most welcome you, sir. Most welcome you, sir. Can you hear, sir?
Thank you.
Yes, sir, you are audible, sir.
Okay,
Thank you,
sir.
Next, yeah, I can hear you.
Next, my sincere extend sincere thanks to Dr. Veerappan Mani, Kingdom of Saudi Arabia, for his wonderful support, his arrangement of his this 101 International Virtual Learning Series. Thank you, Dr. Veerappan Mani, sir. Thank you, sir. Next, I welcome all the respected professors, faculty members, and my dear enthusiastic students for today's session. I hope this session will motivate the students, encourage them in active learning of forthcoming days. So, this is the first and foremost needed for your career. So, all the enthusiastic students, kindly utilize this great opportunity to explore your knowledge. Most welcome. All the very best to all the students. Once again, I welcome you all. Thank you.
Thank you, sir.
Thank you.
Before starting on to the session, I would like to share a few words about our speaker, Dr. Arun Prakash Periasamy, sir. Dr. Arun Prakash Periasamy, sir, received his PhD degree in chemistry with specialization in electrochemistry from National Taipei University of Technology, Taiwan, in June 2011. He was awarded the Taiwan government scholarship for pursuing his PhD degree. He was also awarded Young Scientist Medal in the Advanced Materials World Congress, Singapore. He worked as a postdoctoral research fellow in Professor Chang's Bio and Nano Analytical Group at the National Taiwan University. He then joined as a postdoctoral research associate in the Advanced Sustainable Energy Materials Group of Dr. Anna George Sobrido in the School of Engineering and Material Science at the Queen Mary University of London, and focused his research on oxygen electrocatalysis for zinc air battery development. He is a visiting academic fellow in Professor Tetrisi's Sustainable Carbons Group at the Department of Chemical Engineering in the Imperial College London. He is currently working as a postdoctoral research fellow in Professor Varco's Group in the Department of Chemistry at the University of Surrey. Arun has published 48 research articles, 6 review papers, and 4 book chapters. He is holding 3 international patents. He is currently the guest editor for 2 special issues, graphene-based nanosensors and their applications for the journal Sensors, and disordered crystalline materials for the open access journal Crystals. His research focuses on the preparation of functional nanocomposites, photoluminescence carbon nanomaterials, and semiconducting interfaces for biosensing and photoelectrocatalysis and electrocatalysis. His latest research is aimed at developing radiation-grafted alkaline anion exchange membranes for alkaline fuel cells. With these few words, I would like to invite Dr. Arun Prakash Periasamy sir to deliver the seminar. Please, sir. Dr. Arun Prakash sir.
Thank you everyone for the, thank you for this opportunity. Yes, sir. Can you hear me?
Yes, sir, of course.
Can
yes,
you
sir.
hear me,
Please
sir?
proceed, sir. Please proceed. You can proceed.
So can you hear me?
Yes, sir. Yes, sir. Please, sir.
Okay, sir. Can I proceed?
Yeah, yeah.
Okay. Thank you, sir. Thank you, sir. Thank you, the principal, Dr. Venkatesan, sir, and also the convener and the organizer and everyone for the nice introduction and for this great opportunity. And I also would like to thank my friend Dr. Veerappan Mani for introducing me and giving me this opportunity. So today I am going to talk about the sustainable production of value-added chemicals and fuels from carbon dioxide. So I'm also very good evening for everyone, the faculty members, professors, and students who are watching my talk. So today I'm going to talk about the sustainable production of value-added chemicals and fuels. So carbon dioxide is a greenhouse gas, and we have abundant amount of carbon dioxide in the atmosphere. We are trying to develop some methods to convert this carbon dioxide into value-added chemicals and fuel. So most of my talk today, I'm going to cover about this important electrochemical reactions. I'm an electrochemist and I'm dealing with electrochemical reactions like electrocatalysis, like oxygen reduction, oxygen evolution, carbon dioxide reduction, and hydrogen evolution reaction. Among these reactions, carbon dioxide reduction is a very important reaction and also a very useful reaction. So CO2 emission issues. Before entering into my topic, I would like to discuss the importance of CO2 reduction. We know the CO2 emission is a big issue. This is the video released by the NASA, and you can observe the red like gas or something on the trapping on the atmosphere, and the amount of CO2 released into the atmosphere is increasing day by day and year by year. The figure on the right will show you idea about how much amount of carbon dioxide is released into the atmosphere. For example, in the case of carbon dioxide levels around 1950, and now we can observe a 400 ppm increase in the CO2 level. This huge increase in the CO2 level leads to greenhouse effect. Carbon dioxide is a greenhouse gas, and excess amount of carbon dioxide in the atmosphere will re-emit the solar radiation, and this will lead to greenhouse effect or global warming. Because of the global warming, the global temperature will increase, and this will lead to the melting of the ice or increase in the water level, the melting of ice in the Arctic Ocean and everything. So controlling the carbon dioxide level in the atmosphere is very, very important, and this can be done by different methods. Let's next goes to the what are the important sources of carbon dioxide. There are different sources of carbon dioxide. One is industrial source, power emissions like power grid and industries. They emit large amount of CO2 every day, and flue gas also emits carbon dioxide. Like home and transportation, we use lot of vehicles for transportation, and these vehicles also emit carbon dioxide. These carbon dioxide enter into the atmosphere and pollute our environment. So we have to find some way to convert this carbon dioxide into useful chemical or fuel. One effective way is the electrochemical reduction or electrochemical CO2 conversion. By using electrochemistry, doing electrochemistry, you can convert carbon dioxide into very useful products. Also, the power grid, as I told, the windmills are these are the other sources. What we can do, we can capture CO2 in an electrolyzer, and you can apply some potential, and you can reduce the carbon dioxide into value-added chemicals. You can produce chemical feedstocks like ethanol, methanol, formaldehyde. Different products can be formed. It can be useful for preparing some organic compounds, or it can be used as a starting chemical, and also for the pharmaceuticals as well. It can also be used as a fuel like ethanol. So long-term storage is still a concern. My topic is electrochemical reduction of carbon dioxide. As an electrochemist, we study the oxidation and reduction reaction. So most of the audience may not belong to the electrochemistry background. So I quickly would like to give a basic idea about the reduction or oxidation process. So we know the oxidation and reduction process even happen in the nature. If you see an apple, if you cut an apple and if you keep it in the environment, it will turn into brown, right? It is because of the oxidation of iron present in that apple. So similarly, there are several oxidation process like rusting of iron. So iron will rust and it will form iron oxide. So because of that, you can observe some rust layer on the surface of iron. So these are the natural process of oxidation and reduction. But whereas in the electrochemical process, there are two processes. That is, one is oxidation and the other one is reduction. Simple words, we can say gain of electron is reduction and loss of electron is oxidation. So we deal with electrons because the electricity is the flow of electrons. So we deal with electrons. So the electron can be gained or lost. So if electron is gained, it is called reduction. And if electron is one substance or a metal, if it loses, it is getting oxide. So this is the concept. So we do this electrochemical reduction process in an electronics. This is called a 3-electrode electrochemical system. And in the case of the working electrode is the electrode at which it is a conducting material. You can use any material that conducts electricity as an electrode. The simple electrode material for the electrode purpose is graphite. You can use the pencil, right? So you have the graphite inside the pencil. You can use it as an electrode because it conducts electricity. So, but the material which you use as electrode should be highly stable and it should not degrade or corrode during the process. So what happens means when you apply some potential, electron transfer will happen between the working and counter electrode. So what is the purpose of reference electrode means to the voltage or the potential of the reference electrode will not change during the process. So you can measure the potential of your working electrode with respect to your reference electrode. So always remember the reaction of your interest will happen on the working electrode. The counter electrode controls the flow of electron or to complete the external circuit. So the electrons will flow from working to the counter electrode. The simple example or the best example is glassy carbon working electrode and platinum as the counter electrode. So the electron will flow from the glassy carbon electrode to the platinum counter electrode. So during the reduction process, I said the electrochemical reduction of carbon dioxide. So always the reduction process will happen at the negative potential. There are two kinds of bias. One is positive bias, negative bias. So for oxidation, you have to apply a positive potential or a positive bias, whereas for the reduction, you have to apply the negative potential or a negative bias. Since it is a So how these electrons flow? When you apply a negative potential to your working electrode, you are lowering the potential of your working electrode. So always the electrons will flow from higher potential to lower potential. So when you lower your working electrode potential down, automatically your potential of your counter electrode, that is platinum, will be higher. So the electron will flow from platinum to your working electrode. These electrons will be consumed to reduce carbon dioxide into chemicals. For example, you have to do this reaction in an electrolyte because this is a solution phase or the solution phase process and you need an electrolyte. So basically for this reaction, you have to take a glass cell. You should have an electrolyte which conducts ions. So it should be ionically conductive. You can use any salt like NaCl, you can add into the water. It is an electrolyte because it ionizes into Na plus and Cl minus and it conducts electricity. So during this electrochemical process, we prefer to use the electrolyte that is the bicarbonate solution, potassium bicarbonate solution. Depending on the solubility of your CO2 or carbon dioxide, you can choose your electrolyte. So when you apply negative potential, then automatically your working electrode potential is lowered. So the electrons from counter electrode platinum will flow to your working electrode and carbon dioxide will consume this electron, and you need some protons for reducing this process. So you have water as the electrolyte. Water will dissociate into proton H plus and OH minus, and this proton will be consumed. So basically, for reducing carbon dioxide, you need electron, and this you need electron and proton. Proton you can get from water, and the electron you can get from electric circuit. So how you are driving this electron means you connect these 3 electrodes to a potentiostat, but you can control the potential applied to the working electrode by controlling the potentiostat. For example, -1 or -1.5, and automatically the electron will, if it is negative, if you are applying a negative potential, electron will flow from counter to working, and these electrons will be consumed at the working, and carbon dioxide will react and it will reduce into product. Okay, so this is the basic concept. Whoever not belonging to electrochemistry may understand this concept. So that's why I introduced this one initially before starting my talk. So the best catalyst or a best electrode for the CO2 reduction is copper. Copper-based materials are mostly used for CO2 reduction because it is a good catalyst for electrochemical reduction of carbon dioxide. There are multiple products formed during carbon dioxide reduction. Bear in mind, there are multiple products, not a single product. So what are the products formed during carbon dioxide reduction? Like you can form aldehyde. So basically aldehyde, alcohol and alkenes can be formed. They contain 1 carbon atom, methanol 1 carbon atom, whereas ethylene 2 carbon atom, and ethanol or propanol 3 and 4 carbon atom. So starting from 1 carbon atom product to 4 carbon product, you can form several products in the liquid as well as gas. The first product formed will be CO2 will be reduced to carbon monoxide. Here you can see I have shown here like the reactions which will form, through which the carbon dioxide will be reduced to formic acid, carbon monoxide, methanol, ethane and ethanol. If you observe here the number of proton and number of electron transferred, so by controlling the number of electron transferred and number of proton transferred, you can control your product. For in the case of like if you want to form formaldehyde, it should be a 4 proton 4 electron process. In the case of methanol, our interest is mostly on methanol production, so we have to control the 6 proton 6 electron process. The chart on the right gives you an idea about the electrical input and how much fossil fuel or the electricity per ton is produced and number of electrons produced, or number of electrons consumed. You can always calculate the efficiency. Whenever you run a reaction, you always care about the yield or the efficiency, right? So in this case, we say Faradaic efficiency. Faradaic efficiency is nothing but based on the amount of charge consumed, your product formed will vary. So if the amount of charge consumed is completely converted into the product, then your Faradaic efficiency is 100%. But this is not always the reality. Most of the systems can produce only or yield only 60 to 80% or 90% Faradaic efficiency. None of them can achieve the maximum, that is 100% Faradaic efficiency. For example, in the case of methanol, as I told you, you need 6 electrons should be consumed to form the methanol. In the case of formic acid 4, the Faradaic efficiency varies. And let's think about why we need to synthesize these chemicals or these value added products. What is the necessary? Whenever you do some research as a scientist, you should know what is the reason to do this research, because these chemicals have high market value. For instance, formic acid, it has a 0.6 billion per 1 metric ton, so it has a huge market value. The highest market value is for ethylene, ethanol, and carbon monoxide. So based on the market value, you can tune the product. I already told, if you tune the number of proton and number of electron transfer during the electrochemical reduction process, you can control your product. But this is not always easy. It is highly challenging to get one single product. So this gives you an idea about the energy conversion efficiency or the net emission per metric ton for formic acid, carbon monoxide, ethylene, and ethanol. And how profit is this process, or how profit these chemicals which we produce from carbon dioxide? They're highly profitable chemical. This depends on the how much energy it consumes or how much charge it consumes, and what are the cost you are using for your electrolyzer, electrolyte, electrodes. Everything needs to be accounted for determining the cost. In this case, the highly profitable chemical is carbon monoxide. Carbon monoxide is a poisonous gas, but it has highly industrial value, and it can be used as a starting chemical for producing several other chemicals. Also hydrogen. Hydrogen, we know it can be used as a fuel, so it has also a high profit or a high value added chemical. And ethanol. Of course, ethanol can be used in alcoholic beverages, right? Like wine or other alcohols, you can add ethanol as an additive. And also the ethylene. Ethylene gas can be used for ripening the fruits. With the ethylene and nitrogen mixture can be used for ripening the fruits. So it can be used as a food additive. Formic acid can be used as a food additive. So these are all the value added chemicals which can be used from starting from fuels to even the food industry, additives, and everything for fruit ripening and everything you can use. So these are the profit. This gives you a clear idea about why we need to do this research. But in reality, as I told, the Faraday efficiency is the key factor or the key parameter to determine the efficiency of the electrochemical reduction process. And if you see for ethanol, the Faraday efficiency is only 40, and the partial current density can only reach up to 200. In the case of the formic acid, people are reporting different more higher Faraday efficiency, like 90 or 95%, and the partial current density is 500. So for the industrial purpose, you really need to achieve high current density like 400 or 500 milliampere per centimeter square. This is partial current density. For example, this gives you a rough calculation, but about next 30 years. For instance, pure carbon dioxide price accounts for about $30 per ton, and Faraday efficiency, if you can achieve 90%, and if you can achieve a maximum current density of 500 milliampere per centimeter square using an electrolyzer which you built with a cost of $300 per kilowatts, and the plant lifetime can last for 30 years. This is a huge goal, and we have to focus on this, and we have to construct such water electrolyzer or the CO2 electrolyzer to produce these value-added chemicals. And I will introduce some basic things about the electrochemical cell setup and what kind of electrolyte you can use and what kind of mechanism it happens in CO2 reduction. This can be useful. Usually the electrochemical cell, electrochemistry or electrochemical setup is the one where your reaction occurs, and it is made of a glass or a quartz cell. So in the case, you can use either a single compartment cell or a divided cell. Usually H-type cell is called a divided cell. What is the difference between a single cell and a divided cell? Divided cell is the anode and cathode, or the working and the counter electrode will be separated by a permeable membrane, proton permeable membrane. So I told you are getting the protons from water because water is the electrolyte you are using. These protons has to pass from one compartment to the other. If you have a single compartment cell, always water can be reduced to hydrogen. So hydrogen evolution will dominate. Hydrogen evolution will also occur at your working electrode. This will dominate your CO2 reduction and it will lower your efficiency. So this is the reason why you should have a divided cell. Also, some products will be formed at the counter electrode as well. PT is the counter electrode. You can use graphite counter electrode if you are using an acidic pH. So you have to use these best practices for CO2 reduction. So the main purpose of the proton permeable membrane is proton will transmit or transport from one compartment to the other compartment, and even if hydrogen is evolved in the that is the counter electrode, it will not affect your CO2 reduction. So that is the purpose of, but it will affect your efficiency, but it will not dominate your CO2 reduction. So this is the purpose of the divided cell. In the case of a single cell, you don't have a separator, and everything working reference and counter will be present in the same cell. So what are the technological challenges like high cost, actually you are supplying some potential and you are using a potentiostat, electrochemical setup. So this accounts for the cost. Also, you need a good catalyst. So the catalyst preparation cost also matters. And inferior efficiency, low product selectivity. So selectivity is a huge problem in CO2 reduction because multiple products like C1 to C4 products will be formed during CO2 reduction. Fast degradation of activity, because your catalyst cannot hold for a long time. As I told, it has to withstand at least for 500 hours, 1000 hours. But in reality, like 3 hours or 5 hours or 10 hours, the catalyst will degrade from the surface. So the fast degradation is the important drawback. So the other thing is you are producing the value added chemical, right? So you have to recover that chemical from the electrolyte. That cost also accounts. So you can use a circulated flow like analyte, and you can use a pump to pump that solution from one compartment to the another. By controlling the flow rate, you can also remove the formed products instantaneously, and you can analyze using gas chromatography or other chromatographic technique. Those who working on pharmaceutical chemicals, maybe you use chromatography like HPLC or gas chromatography or NMR to determine the purity of your chemicals. So that can be used as well. The other one is the electrode. So this carbon dioxide is a gas, so you have to feed this gas into your electrolyte. So the solubility of the carbon dioxide is a major issue. So people use highly soluble solvents like methanol. But if you want to produce methanol in your system, then you can't use methanol as your electrolyte. Obviously, you have to use an aqueous electrolyte like bicarbonate solution. So you can feed this carbon dioxide to your working electrode into the solution, but carbon dioxide will not dissolve easily. Alternatively, you can use a gas diffusion electrode. Instead of purging the carbon dioxide into the electrolyte, you can purge into the backside of your electrode, which has lot of pores. The gas can easily pass through the pore and it can deliver to your catalyst surface without the need of dissolving in the electrolyte. So this is the purpose of using a gas diffusion electrode. So you can use a single compartment cell, you can use a divided compartment cell. Single compartment cell have the issue of hydrogen evolution, whereas hydrogen evolution dominating CO2 reduction. But if you have a divided cell, you can use a proton exchange membrane, and the proton can move from the one compartment to the other compartment, and then it can avoid the hydrogen evolution dominating the CO2 reduction, and also the product can also move sometime. And the triple phase you have to consider, like you are using a solid electrode and you are using a gas and you are using a liquid electrolyte. So solid liquid gas interface is called three-phase interface or triple phase interface. So we are studying the reactions occurring at the triple phase interface. And gas diffusion electrode versus aqueous phase electrode. As I told, in the case of aqueous phase electrode, you are feeding the carbon dioxide into the electrolyte, so it cannot dissolve efficiently, and it cannot. So when you pass the gas into the electrolyte, it has to dissolve first, and it has to diffuse through the electrolyte, and it needs to reach the electrode surface. Always a diffusion is an issue and solubility is an issue. Whereas in the case of gas diffusion electrode, you are not passing or purging your CO2 gas into your electrolyte. Instead of doing that, you are purging the CO2 gas at the back of your electrode directly. Because of that, it is not at all, there is no need for the gas to pass through the electrolyte, and it can easily or directly it can feed to the catalyst surface, and it can react by you are applying the potential, it can react and it can reduce and it can form the product. But the things you have to look into it is you are using 100 micrometer electrode, but the catalyst is 10 micrometer, and the reaction happening will be in the nanometer regime. So we have to consider all these things when you are designing your system. So the gas stream and electrolyte stream can be separated using a membrane, and also like using a divided cell can help overcome the pH limitation. So the other reason for using the divided cell is it can overcome the pH limitation, and it can also promote CO2 transport and industrial current density. Here you can see I have shown the nickel nitrogen carbon catalyst using the glassy carbon electrode. In the normal 3 electrode system, it can only achieve 15 milliampere per centimeter square current density. Whereas in a GDE, that is the gas diffusion electrode, it can achieve as high as 223 milliampere per centimeter square. Almost like 20 times you can increase the current density. So gas diffusion electrode is a good system and you can use it to achieve higher current density. And how you can make these electrodes like freestanding carbon support, because you are using the gas, this gas has to pass through your electrode surface. When you have a porous electrode, then the gas can easily pass through the pores and it can increase your efficiency. For example, this is the carbon nanotubes. So everyone know about different carbon materials like carbon nanotube, graphene. These are the 1D and 2D material. And if you use the carbon nanotube, you can arrange the carbon nanotube like a pillar-like structure, like something like your how we are building the house, right? If you have the pillar-like structures, if you use pillars to your house, it can add strength or stability to your house. Similarly, if you have a pillar-like structure nanomaterial, then it can add strength or stability to your structure. Also, it have a lot of pores, so the gas can easily diffuse through the pores. So that is the idea of creating this carbon support. So how you can create this 3D carbon support? So 1D, 2D and 3D. 3D, you can use 3D printer or a 3D printing. You can use some solution. You can mix your whatever nanomaterial you want to prepare. You can mix, you can adjust the viscosity and you can control by a computer and you can just print your structure very easily with lot of pores. So that is the idea of using the 3D printers. So here you can observe the 3D structure printed using a 3D printer. Like polymers are mostly used in the for 3D printing. And electrode spinning is another good technique which can be used to produce something like a fiber, like a carbon fiber, or like if you know carbon cloth, right? So you can electrospin this solution and you can apply some voltage to this solution and you can form fibers and you can collect it, and it is very useful 3D structured material. And why nanostructure materials are needed for CO2 reduction? So you can use a copper foil or a copper metal, but why we need to prepare some nanomaterials, because the nanomaterials are the ultra small, or they have very small size, and because of the smaller size they have the high surface volume ratio and high surface area. So once you have your catalyst with a high surface area, then the reactants can react efficiently on your catalyst surface, and it can produce efficient products in the efficient way. So the particle size effect, by lowering the particle size, like here you can observe on the left, like 4, 6, 8, and 10 nanometer gold nanoparticles. For instance, for the 4 nanometer, the black one, you can observe the high current density. So whenever you have a smaller nanoparticle, you are increasing the surface area and the activity can be increased. And oxide derived film effects. So these are the different kinds of effects. Like copper, you can form the copper nanomaterial, copper nanoparticle, copper nanowire. You can also oxidize the copper and you can form cuprous oxide or cupric oxide. So depending on their oxidation state also, the activity can vary, and depending on the shape or structure, like a particle can be like a sphere, it can be like a nanocube, octahedra, it can be like a nanowire. So depending on the structure or the shape or the crystal facet, actually you are tuning the active site, and this helps for the increasing your activity. And defects and anisotropic effects like edges and corners. For instance, if you have a bulk material, it won't have many edges, so the active sites will be very less. But if you create some zigzag edges or corners, then you can increase the activity several folds. So this is for nanowires, like based on the nanowire length, like 15 to 500 nanometer, you can increase the activity. So depending on the nanoparticle size or the nanowire size, you can tune the activity. Depending on the oxides, you can tune the activity, and depending on the defects or anisotropic effects, you can tune the activity. And this is for the bulk copper. As I told, the product selectivity is very poor for the bulk copper, it forms several products like hydrogen, methane, formate, carbon monoxide, and ethylene. So what is the drawback in forming different products? Once you have multiple products, then you cannot separate each product from your electrolyte. That becomes a huge challenge and a drawback. So you have to prepare or produce a single or two product, then it will be easy to remove or isolate the products by either chromatographic techniques or distillation you can use. So the choice of electrolytes. So far I have introduced about the cell, what kind of electrochemical cell you should use, what kind of electrodes you should use, and next we move on to the choice of electrolytes. There are two kinds of electrolyte. One is aqueous electrolyte, other one is non-aqueous electrolyte. Aqueous means aqueous electrolytes have the water as the medium, whereas non-aqueous electrolytes does not contain any water. So if you have the aqueous electrolytes, mostly they are prepared using alkali metal cations like sodium and potassium. The best examples are sodium bicarbonate, potassium carbonate, potassium chloride, and potassium hydroxide. So the best electrolyte used so far is potassium bicarbonate. Most of the people who are working on CO2 reduction, they use potassium bicarbonate. Non-aqueous electrolytes can be used to increase the CO2 solubility, because CO2 will not dissolve easily in aqueous electrolyte. So people are trying to use non-aqueous electrolyte without adding any water. They use non-aqueous. Organic solvents can be used as the non-aqueous electrolyte. In organic solvents, CO2 dissolves in a much more better than how it dissolves in the aqueous electrolyte. So the main reason is, when you use a non-aqueous electrolyte, you don't have water. So there are no proton source. If no proton source means hydrogen will not be produced. So you are able to suppress your hydrogen evolution reaction by using a non-aqueous electrolyte. So what are the non-aqueous electrolytes available? Like DMSO4, dimethyl sulfoxide, and propylene carbonate. So also dimethyl formamide. These are the organic solvents. Those who work on organic chemistry may very well know about these solvents. These are common solvents like dimethyl sulfoxide or dimethyl formamide. In DMF, carbon dioxide dissolves almost 20 times higher than the solubility of carbon dioxide in DMF is almost 20-fold higher than in water. So if you want to have a better system or better solubility, then you can go for non-aqueous electrolyte. But then you have to choose your reference electrode depending on the electrolyte. If you use a non-aqueous solvent, you have to use a non-aqueous reference electrode. That is usually acetonitrile we used to fill in the compartment of the reference electrode, that you can use as a non-aqueous reference electrode. And imidazolinium cation containing ionic liquids. Those who are working on organic chemistry or pharmaceutical chemistry, you may hear about ionic liquids. These are the imidazolinium ion containing compounds, and they have high conductivity. So that's the reason for using ionic liquids. So what is the purpose of using these imidazolinium cation containing ionic liquids? So this can lower your CO2 reduction over potential, and also it can reduce the energy of the intermediate. And main thing is there is no water, so it can inhibit HER, and it can boost your selectivity for CO formation. And also when you select your electrolyte, you need to care about the concentration of your electrolyte, and depending on the electrolyte, also the kinetics. This is the Tafel plot. The slope of Tafel slope also varies. So for instance, the lowest value if you see is for 115 millivolts per decade is observed in the case of bicarbonate and KCl. That's why I told people are mostly using bicarbonate as an aqueous electrolyte, because the kinetics is more favored in bicarbonate for CO2 reduction. Whereas in the case of potassium carbonate or potassium hydroxide, the Tafel slope value is higher. Always when you have a higher Tafel slope value, it means the kinetics is poor. And if you have also different mechanism will happen. So if it is if the Tafel slope is lower, this is 115 millivolts, it is close to 120 millivolts. So the kinetics is much more favored. And also depending on the pressure, so the real atmospheric one atmospheric pressure, right? But when you do this reaction in a closed cell, and if you control the pressure by changing the pressure and also by changing the electrolyte, you don't need to use higher concentration of electrolyte. For in this case they use potassium hydroxide. If you see the black curve, that is for the 1 molar potassium hydroxide. When you increase the concentration, then the Faraday efficiency actually drops. So it is preferred to use 1 or 2 molar electrolyte is enough for the CO2 reduction, not more than that. The concentration of the electrolytes should not exceed more than 1 or 2 molar. And here you can see the pressure scale. With increase in the pressure, also the Faraday efficiency increases. But whenever you are dealing with pressure, controlling the pressure, you should be very careful. And solvents and supporting electrolytes in the electrocatalytic reduction. So already I told about the solvent. So when you are using a solvent, you have to consider about the salinity, pH, and these are the chemistry people may know about this. When you have an electrolyte, you care about the pH, salinity, solubility. So depending on this, for instance, in the case of if salinity is 0, then the concentration of CO2 dissolved is around 4. But if it is the salinity is around 35, the much more higher concentration of CO2 can be dissolved. And also depending on the pH, the solubility of the CO2 changes. So you have to pay attention to these pH changes. Local pH changes or pH changes. And this is the Pourback's diagram. So those who are working on the inorganic chemistry or the material chemistry, they may hear about the Pourback's diagram. It is nothing but you are monitoring the electrode potential with respect to pH. So depending on the pH range, your electrode potential will change and also your species will change. For instance, in the case of bicarbonate, the pH will be around 6 to 7 if you use a bicarbonate electrolyte. So predominantly you will have a bicarbonate ion in your solution. So this will gives you an idea about what kind of mechanism will happen in during your electrochemical reduction of carbon dioxide. So the pH change is very important. The other important thing is carbon content and also bubbling before and bubbling, because you are bubbling the CO2 into your solution, and this can, before and after bubbling the CO2 into the solution, the pH will change. So before bubbling your carbon dioxide purging your carbon dioxide into the electrolyte, the pH may be higher. For instance, you can observe for the potassium hydroxide. We all know potassium hydroxide is a strong alkali, right? The pH will be 13. So before bubbling it is around 14, but after bubbling it drops to 8. So you can imagine the pH change from 14 to 8. So almost it becomes half. So you shouldn't consider the initial pH. Okay, potassium hydroxide has a pH 14. You should not consider that pH for your calculation. So you have to measure your pH after purging your CO2 or after saturating your electrolyte with CO2. Almost every electrolyte, the pH will drop a bit. Like for potassium bicarbonate, from pH 9 to pH, here you can see for potassium bicarbonate, 0.5 molar bicarbonate and 1.5 from, it will drop from pH 8 to 7 or 6. So depending on the pH, you have to consider the pH after saturating your solution with the CO2. And electrolyte, you have to consider the basicity, Lewis basicity, and cation, anion, and also how the cation hydrolysis occurs and specific adsorption and CO2 saturation. So whether it is protic or aprotic, these are the things you need to consider and make sure everything is okay. And the role of electrolytes in CO2 reduction. So we use bicarbonate as the electrolyte, and when you use bicarbonate, it enhances the rate of CO production. So carbon dioxide will be reduced first to carbon monoxide through a 2 proton 2 electron process. So this process can be enhanced in the presence of a bicarbonate electrolyte. So dissolved CO2 is the primary source because you are going to reduce carbon dioxide. So CO2 is obviously the primary source of carbon. So whatever your carbon found in the solution comes from carbon dioxide, not from bicarbonate. Okay. And the effective concentration of dissolved CO2. So you may have a lot of carbon dioxide in your bulk electrolyte, but that will not react with your electrode. So only the carbon dioxide which diffuses and moves near your electrode, and that electrolyte interface at which carbon dioxide reacts will only accounts for the CO2 reduction. This you have to bear in mind. That's the reason for using a gas diffusion electrode. And the equilibrium between the bicarbonate ion plays a major role role and the concentration of the electrolyte. Based on the bicarbonate concentration, the current density may vary. And also the if you have a electrolyte interface, you will have an inner Helmholtz, outer Helmholtz plane. So those who work on electrochemistry may know about this. And this is the charge accumulation or a double layer formed at the electrode-electrolyte interface. And when you add some other counter ions like cation or anions like supporting electrolyte into your, for example, if you have a bicarbonate electrolyte, you can add potassium chloride, potassium bromide, potassium iodide as the counter ions. So depending on the counter ion you introduce into your electrolyte, the solvation cell or the hydration cell may change, and depending on that, your Faraday efficiency may drop. For instance, when you use only on the right, you can see this plot. I hope you can see this plot. If you use the 0.1 molar bicarbonate solution, the black one, you don't observe around 40% efficiency, but you can observe for the blue curve, that is the 0.3 molar potassium iodide. So the Faraday efficiency increases from almost 30 to 60. So depending on the counter ion, the solvation shells will change, and this can increase your Faraday efficiency. So go for good cation or anions which can increase your Faraday efficiency. And what are the other factors influencing the reaction kinetics? When you have an electrode, you have your electrolyte and the diffusion layer. So the diffusion layer is from the bulk to your electrode interface. There will be a concentration gradient will be developing. For instance, the CO2 in the bulk solution will be much more higher, but the CO2 near your electrode surface will be very less. So from always the whether gas or potential or everything will move from the higher concentration or higher potential region to the lower. So similarly, in your electrolyte, the saturated CO2 from the bulk will move towards your electrolyte, that is from higher concentration to lower concentration. So because of the difference in the concentration, a concentration gradient will develop near your electrode surface, and this contributes to the diffusion layer, that is 40 to 200 micron thickness. And this migration layer will be only about 0.5 to 5 nanometer thickness. And depending on this diffusion layer and migration layer, this entire process of CO2 reduction may vary. Like starting from CO2, it can form the CO intermediate, CO observed intermediate, and it can form the carbon monoxide, and then it goes on further for the producing other products. And electrode surface region, mass transport layer, and bulk solution are playing major roles. And electrocatalyst with optimum catalyst layer thickness. So I told you should have 0.5 to 5 nanometer as the migration layer and 40 to 200 micron thickness as the diffusion layer. So if you have a bulk material, then this diffusion layer and migration layer may change. So always try to have a thin layer of the catalyst, then you can have a very thin migration layer and the diffusion layer, and your reaction may be more efficient. So the diffusion and concentration profiles are very important, whereas in the boundary layer is also plays a major role. And if you have a smooth electrode surface, the boundary layer will be different. If you have a curved and porous electrode, then the boundary layer may be different. You have to consider all these, and depending on that, the pH, local pH changes may change depending on the boundary. So we have to consider the electrode, reference electrode, counter electrode, electrolyte. What are the counter ions you add into your or you introduce into your electrolyte, and what are the local pH changes happen during the CO2 reduction. And next we move on to the value-added products, that is the value-added chemicals. Why methanol production is important? So here you can see the plot that CO or the syngas or methane or methanol, ethylene, ethanol, propanol. So methanol has a high market value. Similarly, ethanol, ethylene, acetaldehyde, and formic acid, you can see a huge market value. I already introduced in my second or third slide. So when you prepare a highly value-added product, then you can sell your product industrially. So if really your system has a good potential for industrial application, then you can produce that. You can reduce carbon dioxide, and you can produce even formic acid, and it can be reproduced, or it can be patented in a company, and then you can go for the patenting and everything. And this gives you an idea about the catalyst and the CO energy. These energies are calculated using some theoretical calculation, and you can observe the energies for different materials and also the hydrogen adsorption energy. So always when you have a lower adsorption energy, it is better. So depending on the adsorption energy, you can tune the activity. Why copper-based catalysts are mostly used for CO2 reduction? Because the copper is the only metal which has, you can observe the scale on the bottom and also on the top, on the left. So the scale on the bottom gives you an idea about the adsorption energy, delta E of hydrogen adsorption, and this one gives you delta E of carbon monoxide adsorption. So copper is the only metal, so that's why we put the cross here, and you can observe the cross for copper, that is around 0.2 or something. So, but whereas if you see the other metals, they are mostly negative. So they have the negative delta E for CO as well as for negative delta E for proton, that is the H plus. But whereas the copper is the only metal that can that has the positive value for the proton and also the positive value for the positive delta E for the carbon monoxide. This is the reason why people are using copper-based catalyst for the CO2 reduction. Also, several other materials are also used. And selectivity criteria for methanol production. So let's move on to the selectivity. I told you it is a big challenge. How you can control your selectivity? So far I introduced what is a CO2 system and several things I have discussed. But next we move on to the selectivity. So you are using an aqueous electrolyte, you have proton, so the protons will adsorb. The hydrogen binding strength is very important. If hydrogen or proton gets strongly adsorbed, then it will be reduced back to hydrogen. So the hydrogen evolution will dominate your CO2 reduction. Strong hydrogen or the strong proton binding leads to high hydrogen evolution reaction activity. So low selectivity for CO2 reduction. So when you want to achieve high selectivity for CO2 reduction, then obviously you have to suppress your hydrogen evolution reduction. So this can be done by minimizing the hydrogen adsorption energy. When your catalyst have high hydrogen adsorption energy, then it will obviously produce hydrogen instead of reducing carbon dioxide to carbon monoxide. So try to lower your hydrogen adsorption energy or binding energy. Metals including copper have high hydrogen binding strength, because even though copper have some unique properties like positive delta E for proton and positive delta E for CO, it also have high hydrogen binding strength. Because of the high hydrogen binding strength at a copper electrode surface, mostly hydrogen will be produced rather than reducing the carbon dioxide to other products. Still, copper is a good catalyst, but hydrogen evolution will dominate the CO2 reduction in the case of copper-based catalyst. And people are trying to develop some metal nitrogen catalyst, like you can use titanium nitride or other nitride-based compounds. Like even people are using Mexin recently, 2D material, titanium nitride, titanium carbide, titanium nitride. You can use different nitrogen-containing sites. So the main reason for preparing the nitrogen-containing nanomaterials is the nitrogen site can enhance your local CO2 concentration, and that can increase your CO2 reduction. So the CO2 selectivity trend for different metals. So nickel is the best, iron, manganese, and cobalt. All of them will only be equal to copper. And pyridinic site. So if you have a nitrogen site, it can be different types like pyridinic nitrogen, pyrrolic nitrogen, and quaternary. Depending on the number of rings in the benzene ring in which the nitrogen is getting attached. If it is attached to a 6-membered ring, it is called pyridinic. If it is 5-membered, it is pyrrolic. So depending on the benzene ring in which number of rings in which it is attached, you can determine the pyridinic or pyrrolic nitrogen. Depending on that, selectivity may change. And this gives you an idea about the free energy for different metals and metal nitrogen-based catalysts. So metal nitrogen-based catalysts have positive, similar like copper, they have positive proton adsorption energy and positive delta E for the COOH. Similarly, they have the positive values for proton and CO. And if you see the different carbon-based materials compared to the pristine graphene, pyrrolic nitrogen containing one are performing well, and they have the lower energy. This is the energy delta E for COOH. So whenever you have a minimum energy, it is better. So the pyrrolic nitrogen containing the nitrogen site containing materials are performing better than the pristine ones without the nitrogen site, and this applies to the graphitic, pyridinic. So if it is applied to a graphitic carbon, it is graphitic nitrogen. So different types of nitrogen you can tune. As I told, you can see here graphitic nitrogen, pyridinic nitrogen, depending on the number of rings. Okay. And weak OH binding, similar to hydrogen binding and also CO binding, OH binding strength also determines the methanol selectivity. Depending on the OH binding strength, you can either produce methanol or methane. And CO binding strength also determines your product selectivity. For instance, if you have a hydroxyl binding strength, if it is negative value, your CO2 will be reduced preferably to methane instead of methanol. If you can tune the hydroxyl binding strength to a more positive value like 0.4, 0.4 or 0.8, then you can get methanol instead of methane. So this is how you can tune your selectivity. So one thing is you can tune the binding energy for CO, binding energy for proton, binding energy for OH. Always try to have the minimum binding energy other than cases like methanol. In the case of methanol, you should have a positive energy rather than the negative OH energy. Delta E value. Okay, and what are the active metals used for methanol production? Titanium, molybdenum, ruthenium. These are the transition metals mostly used for the producing methanol, and this is the cell setup used for methanol production. You will have a divided cell, and you'll have a reference electrode working and counter, and you'll have a membrane separating these electrodes. And this is an electrolyzer. This is how the cell will be looking in the real industrial application, like a fuel cell stack. So you will have a compartment, and it will be separated by a membrane, proton exchange membrane, and you will have a stack, and you will hold them with a bolt, and you can observe here. So they have the bolt and the quartz thing and the fuel cell stack, and your membrane will be in the middle, and you will have your working, and here you can have the two electrodes working and counter, and you can put reference if needed. And these are the methanol selectivity data reported in the literature. You can observe some reports have reached 100%, but most of them are around 50 to 60%. So still there is a room for improvement, and still there is a room for developing new catalyst. And methanol and ethanol, you can observe different material like bulk copper. The methanol selectivity is very poor. That's why people try to develop nanostructured copper, and alloys like cobalt, gold, and nitrogen-based carbon fibers can yield higher Faraday efficiency. Basically, instead of having a bulk material, if you have a nanomaterial, you can achieve higher CO2 reduction efficiency. But selectivity, you have to consider those adsorption energy for proton, carbon monoxide, and also hydroxyl ion. And methanol selectivity of copper oxide and copper interfaces. Compared to copper, if you see for methanol, the selectivity is much higher. Even the Faraday efficiency, if you see at the bulk copper, it is only 5%, whereas for the methanol production, not Faraday efficiency, methanol production, if you see 50 micromoles per ml, whereas at the bulk copper, it can only yield around like 2.5 to 3 micromoles per liter. So compared to the bulk material, the catalyst like copper oxide or cuprous oxide is a very good catalyst. And as I told before, instead of using a normal electrode, if you use a GDE gas diffusion electrode, the performance increases significantly from almost like twofold, like 30, as I told, even 10-fold also increment is possible to achieve. In the case of cuprous oxide, zinc oxide system, they have achieved around twofold from 30 to 60% Faraday efficiency. So go for gas diffusion electrodes. And in our recent work, this work we did in 2018 at National Taiwan University, we tried to prepare some flexible freestanding paper electrodes. And we want to introduce some nitrogen site in our catalyst, because nitrogen containing sites can increase the CO2 local concentration. So this is a commercial paper, and it was very cheap, like the normal paper, fiber paper, and we soak in a organic compound like pyrrole, and we introduce this into a copper solution. And because of the metal to ligand charge transfer, that is from copper to pyrrole, so the polymerization of pyrrole will happen, and it will form polypyrrole. And polypyrrole has a nitrogen attached to the 5-membered ring, and this is good for CO2 reduction. The main advantage of this one is because it has a fiber and it have lot of pores, this can actually act as a GDE, literally like mimicking, not like a exact GDE, but it can mimic like a GDE, gas diffusion electrode. And this is highly flexible, and here you can observe the fiber electrode after coating with copper-based material. Mostly copper-based material or cuprous oxide or cupric oxide are brown in color, mostly the cuprous oxide, so you can observe the brown color. So when you have a fiber electrode and you are feeding your carbon dioxide to the fiber surface directly, and much more efficient way we can get the CO2 reduction efficiency. This is the morphology of the particles which we prepared in this work. Like we can prepare like a flower-like structure of, as I told, instead of having a bulk material, if you go for nanomaterial or micro-sized material, this is a micro-sized material, microparticle, but it have different facets, and this helps to achieve higher selectivity. We can prepare either flower with one single octahedra like here, or with multiple octahedra. This is the morphology, and you can observe the activity. You can control the potential applied to your electrode, working electrode, by using a potentiostat, and you can use a technique like cyclic voltammetry. So cyclic voltammetry, you are sweeping the potential to the more negative potential, and you are sweeping back again to the initial potential. When you do this in an CO2 saturated electrolyte, you can observe a increase in current with increase in CO2 reduction. The blue curve is for the composite paper with the flower-like morphology, whereas the cyan one is for the cyan colored one, curve is for the octahedra shaped particles. So almost twofold we can achieve higher CO2 reduction activity. Also we confirm this by using impedance analysis, and the conductivity is much more better for the octahedra, the composite one, rather than the octahedra one. So you can observe here there is no semicircle in this region for our composite paper, and the size of the particle is around 4 to 5 microns. It's not a nanoparticle, but still the activity is good because it have high index phases like 111, 31, 311, and 211. So when you make a nanomaterial, micron or nano-sized particle, if you have defects like zigzag edges, or if you have some high index phases, then you can increase the activity because you are lowering the absorption energy of hydrogen or CO. That's why you are getting higher selectivity. In our case, we analyze the product after applying that potential like minus point. Here you can observe the potential which we apply like minus 0.45 to minus 0.95, and depending on the potential applied, you can tune the Faraday efficiency. And this is the GC graph, gas chromatogram. You can observe blank, there is no signal for methanol, but after CO2 reduction, you can observe a peak for the octahedra shaped particles on the paper electrode. But this one is almost 2 or 3-fold higher for the composite paper. And we quantified our product using GC, and we confirmed we got a single product methanol in our liquid system, and the activity of the composite electrode is almost 2-fold higher than the only octahedra. So that's why I told, depending on the shape of the particle or the size, you can tune the activity. And gas product. So when you are dealing with CO2 reduction, CO2 is in the solution, but still it will generate some gases because it is a gas, right? So when it is getting reduced, it will also form some gaseous product other than the liquid product, C1 product like methanol. It will form carbon monoxide. That this we confirmed by again using gas chromatographic analysis. We got, this is for the standard carbon monoxide. We injected standard carbon monoxide and we got the signal, and at the same retention time we got the signal for our product, whatever gas we collected in our system, headspace of our system, and we confirmed that it is a gas from the using the calibration plot. We did the electrolysis for 1 hour. We also did for 15 hours, and we found it was really stable. And we also, as I told, hydrogen evolution is dominating your CO2 reduction. This you can confirm by gas analysis, gas chromatography analysis again. In our case, we observed only a small peak for hydrogen, and even at minus more negative potential, the hydrogen evolution is suppressed. This may be because of the polypyrrole coating, and also the nitrogen present in the polypyrrole and increases the CO2 CO2 concentration, and this help. Also, we have the high index facets. And we also did NMR for to confirm the product methanol. We used the deuterium oxide as the solvent, and you can observe for the this is for the composite, and this is for the octahedra. Compared to the octahedra, we almost achieved twofold, and this was comparable to the 3.2 ppm, the shift which we observed in the NMR for the product which we produced in our system. And there are several mechanisms for CO2 reduction. You can look into the literature, and you can understand more about the mechanism, what really happens at what is really happening at your electrode-electrolyte interface during your CO2 reduction. But quickly to sum up, the mechanism occurring in an aqueous electrolyte and ionic liquid electrolyte and non-aqueous electrolyte are totally different. So you have to bear this in mind. So every intermediate formed has a rate determining step, and we have to consider this rate determining step, and also the local pH changes has to be considered. In the case of CO2, aqueous electrolyte CO2 will be converted to carbon monoxide first, and then it will be proceed like a multiple electron pathway, either through C1 pathway or C2 pathway, and it will form methane or ethylene. And the reason for using the ionic liquid is it will increase your CO2 concentration, because these ionic liquid have imidazole ions, cations, and these cations can absorb the CO2, and near your electrode, if you coat your electrode with this ionic liquid containing catalyst, then these catalysts can automatically absorb lot of CO2 on their surface, and they will increase the local CO2 concentration. And because of that, imidazole cation also stabilizes the intermediate, that is the CO2 radical intermediate, and it leads to CO production. So it increases your CO production. In the case of non-aqueous electrolyte, different intermediates are formed, like oxalate and also like glycolate. Different products will be formed. These are the two processes, like oxalate desorbs. So basically these mechanisms or these mechanism occurs either through the adsorption or desorption. Adsorption means attaching. Like on your catalyst surface, the intermediate form will either attach or detach. So attach, detach is called adsorption and desorption. Because of this process, you can control your selectivity. Okay. And in situ monitoring of the reaction intermediate. So you have to think about what are the I told about the intermediate and adsorption and desorption. So you need to monitor what kind of intermediate is formed in your system. This you can use like chromatographic techniques, or you can use some in situ FTIR or in situ Raman techniques. Like you can position your working electrode, and you can position your laser beam or mirror. You can set up this system, and then during your electrochemical reduction, what is happening or what kind of intermediate is formed, you can monitor. And also infrared spectroscopy you can use, and you can monitor different products. In situ FTIR you can do use, and also you can use external reflection or internal reflection technique to monitor the intermediates. And post analysis. So after CO2 reduction, you have to still check your catalyst, whether your catalyst is still stable or not. How you can do that, or how you can confirm the stability of your catalyst. So run your CO2 reduction for 1 hour or 2 hours or 3 hours. After your CO2 reduction, just collect your catalyst and you go for some spectroscopic analysis. We did the Raman analysis and XRD, and this is for the cuprous oxide, and we did for cuprous oxide polypyrrole fresh one, that is the black one, and almost we aged that electrode in air for 1 week, 4 months. We left the electrode in air for several months. Since the cuprous oxide have a polypyrrole coating, it didn't get oxidized, and because of that the cuprous oxide is really stable, and it can exhibit all the peaks for the basic cuprous oxide or the fresh or the pristine cuprous oxide. And similarly, we also monitored the polypyrrole peak, and we did not observe any difference in the polypyrrole peak. So it means the polypyrrole remains stable in air when exposed to air after several months. And also we did the XRD spectrum, collected the XRD for before and after electrolysis for 10 minutes, 30 minutes, 1 hour, and also for different catalyst, and we confirmed that there is no significant change in our high index phases. As I told, the high index phases are mainly responsible for the selectivity for methanol, and even after electrolysis we observe these high index phases. It means the catalyst is stable. And we also did SEM post characterization, and we did not observe any significant change in the polypyrrole thickness. You can observe the polypyrrole thickness, and also the size was almost same. And we did high resolution TM and SAD patterns, and we almost got all the diffraction pattern, and also the polypyrrole thickness you can see for like 5 to 6 to 7 nanometer thick. After CO2 reduction also is still is 6 to 7 nanometer, and we can retain the diffraction spots for the copper. Confirm the material is stable. And finally, what are the future challenges and solution? So whoever works on CO2 reduction, or whoever plans to work on CO2 reduction, he has to think ahead and what are the goals he need to achieve in CO2 reduction. Like there are several challenges in CO2 reduction, like degradation mechanism of copper-based catalyst is a huge issue. So you can start from here, like the catalyst can degrade, it can dissolve or dissolution will happen, and the catalyst may reshape, and Ostwald ripening will happen, and also fragmentation. Fragmentation means just like breaking, and the break or the broken fragments can agglomerate again. So this is an issue. So you have to monitor all these processes and to improve the stability of your catalyst. The other main drawback is multiple products are formed because it is a multiple proton and multiple electron transfer process. So the selectivity is the issue. So when you want to produce a C1 or C2 product, you have to control the proton and electron transfer. Another huge challenge is how we are going to get the energy driving for the CO2 process. Instead of using a normal electrocatalyst, you can use a photo electrocatalyst, and we can use the solar light as the source, and you can shine your catalyst surface with the solar light, and you can drive the CO2 reduction process using the solar light. And because of CO2 reduction, you can produce electrofuels, and it can be used for the vehicles, like ethanol can be used as a fuel for gasoline production, and several things can be used. But the main challenge is, if you see the PV power or photovoltaic power, it is only available at the maximum peak can be reached only at the 12 noon, right? After the morning or the evening time, the solar radiation will be not that much intense. So you cannot achieve high intense solar radiation during the morning from starting from 1 a.m. to 12, and similarly from 1 p.m. to 24 hours. So we have to think ahead how we are going to store the solar energy, what we get during the peak hours, and how we are going to use this stored solar energy for running this or driving this reaction. That is a big challenge. The other challenges you have to think about is low reaction kinetics, low selectivity, because multiple products are formed, and competitive hydrogen evolution reaction. You have to minimize the proton adsorption energy, then you can overcome the hydrogen evolution reaction. And cost effectiveness, how effective or how low cost catalyst you are going to prepare, that matters, because these are all industrial process. You cannot prepare a catalyst with like $1,000 or more than that. So then you are putting you can't put a lot of money for producing a single chemical. So you have to consider the cost and stability. Once you put all these costs, and if your catalyst degrade in 5 hours or 10 hours, what is the purpose of preparing that catalyst? It has to work at least for 500 hours or 1000 hours or more. So highly efficient catalysts are needed, and targeting large scale application. This is like lab scale process we are doing, but we have to think ahead how we are going to do this process in an industry, how you are going to capture carbon dioxide from atmosphere, and how you can convert the collected or the stored carbon dioxide into a useful value added chemical by using this solar energy or electrical energy. That will be a huge goal or huge challenge, but that will be really awesome, which when we can achieve in next 10 or 20 years, but hopefully it should be achievable. And efficient CO2 adsorption is, if you have a porous catalyst, you have to avoid the oxidation or durability. As I told you, can have a core shell structure like polypyrrole coating, and you can increase the stability and electrolyte diffusion and different kind of material and selectivity and electron penetration all matters. And take home message finally, what are the key things you have to focus? I'm coming to my end of my presentation, so I want to sum up my presentation. I have talked about several things, like starting from the basic about oxidation reduction to what kind of cell you want to use, what kind of electrolyte, and what is mean by gas diffusion electrode, why we need gas diffusion electrode, and what are the process happening during CO2 reduction, multiple proton electron process, and how many products are produced, and how you are going to separate, how you are going to monitor the intermediate. There are several things, and local pH changes. Okay, I'm going to sum up all this quickly. And higher activity. So when you want to get a higher activity, you have to focus on the electrolysis environment is main thing, and the nanomaterial size, shape, and also grain boundary effect, phase set effect, and also surface tailoring, oxide derived effects, morphology effects. Instead of having a nanoparticle, you can prepare a nanowire or a dendrite-like structure. More porous structures are more efficient for CO2 reduction because of the efficient CO2 transport. And cation effect and anion effect and pH effect, local pH effect, and grain boundary effect. These are all the effects when you consider, if you have to consider for the best practice and to get best results. And points to note, when you are dealing with a full cell like electrolyzer, CO2 electrolyzer instead of a half cell, you have to consider the electrolyzer configuration, cost, and electrode structure, electrolyte selection, pH control or the pH changes, and the electrolyzer's operating pressure and temperature. Because based on the pressure and temperature also your activity will change or your yield will change. So you have to focus on that. So local dissolved CO2 concentration, pH gradient, and GDE to address mass transport issues, and these binding energies. When you want to understand about your mechanism, then you have to do some theoretical calculation like DFT and try to grab that absorption energy information for your catalyst before doing the experiment. That will be very helpful. So you have to grab the information for the hydrogen absorption energy, OH, and hydroxyl and carbon monoxide binding energy strengths. And using anions with a lower buffering capacity is preferred for improving the selectivity. Purity of the always best practices are recommended, whether it is electrocatalysis or organic chemistry, material chemistry, doesn't matter, but best practices always yield best results. Bear this in mind. So purity of the components matters. Whatever you use electrolyte should be highly pure. It should not contain any trace metal impurities. If your electrolyte has some trace metal impurity, then you may not know whether your the trace metal impurities present in your electrolyte is really catalyzing the reaction or your catalyst. So before doing this reaction, purify your electrolyte or get the pure form of the compound from the either Sigma, Aldrich, or any good chemical company available. You can get it with a 99% pure or a high assay product, and then you can prepare your electrolyte. Kinetic measurements are very important for understanding the electron transfer kinetics, and specification of methodology is very important. There are different methodologies available in literature. You have to find the best one, and you have to use that methodology for calculating the turnover number, turnover frequency, electrochemical surface area. These are the key descriptors of CO2 reduction activity. So you have to care about these parameters, and how you are going to, which method you are going to, which best method you are going to use for your calculation also matters. And selectivity, catalyst deactivation, and comparison and control. Control experiments are very important. When you have a bimetal or trimetal, then you have to do the controls for a single metal without catalyst and bare electrode. Everything you have to do controls and make sure any experiment, any chemist or a physicist or whoever have to do more control experiment to confirm the performance. And conclusion, care must be taken while this is the take-home message for you all, that care must be taken while selecting the materials, electrolyte counterions, and GDE for CO2 reduction. Attention should be paid to local pH changes, mass transport, surface roughness, and grain boundary. Freestanding GDE is much more efficient than the normal bulk electrolyte and is efficient, good choice for CO2 reduction. Mass production of flexible paper electrodes is cost effective. If you use carbon paper electrode or some paper electrode instead of a metal electrode, you are actually putting less cost or low cost so that also matters. And conductive and faceted core cell particle. Instead of using a bulk metal, always go for nanomaterials like a hollow structure, nano-sized material, micron-sized material, different phase shade, high index, low index. You can tune that, and also core cell structure. These all can tune your activity, oxidation. How much it can oxidize can also you can control, and it can control, you can control the stability and catalytic activity. Coating the catalyst surface with nitrogen containing polymers is very important because it increases the local CO2 concentration. Improving the selectivity and stability are very important for increasing the Faraday efficiency. Finally, I'm special guest editor for the 2 special issues for the journal MDPA. This one is for the sensor and crystalline materials. I welcome all of you to those who are working on either graphene-based materials or crystalline-based materials for the submission, and the deadline for the first special issue is on 13th December, and for the second one is 28th February 2022. So finally, I would like to thank my supervisor, my PhD supervisor, my postdoc supervisor, our collaborator, Dr. S.M. Sendilkumar sir, and from SICRI, and also my PhD supervisor, Professor Chen from National Taipei University of Technology, and Professor Chong from National Taiwan University, and my current supervisor, Professor John Walko from University of Surrey. And I also would like to thank the conveners, and especially the principal, Professor Dr. N. Venkadeshan, and the organizing secretary, Mrs. R. Kalishwari, and especially the program coordinator, Professor J. Anburaj. I am very thankful for you for organizing this event, and thank you all. I would like to thank my group and everyone for the support. Thank you.
Thank you, Arun Prakash sir. Thank you very much for your wonderful presentation. We had a wonderful and informative presentation.
Thank you, sir.
Any questions from students? Students, don't hesitate to ask. If you have any doubt.
Yes, sir. Yeah. But like you can have plants like, okay, so if you have a plant, you can grow, obviously it's a good question. So like the natural process. So natural process, you can, the plants will consume carbon dioxide in presence of sunlight, it can form starch. The main thing is only you can convert CO2 into starch. You cannot produce these value added chemicals. Okay, you cannot ask a plant to produce a methanol. You cannot ask a plant to produce ethanol or propanol. But industrially, these chemicals are very important. And also, you are not using any carbon dioxide stored in the cylinders or something. Of course, we use in the laboratory, but in the real case or the industrial purpose, if we can collect the, it is excess carbon dioxide in the atmosphere, right? A lot of carbon dioxide is emitting into the atmosphere, and it is also creating a global warming and global pollution. So why don't we use that, consume that, or store that carbon dioxide, and we are only converting. Also, as I told, you can use a minimum electrical energy, you can develop an efficient catalyst. In that way, you can reduce the cost. Also, you can use solar energy. Solar energy is abundant, right? Sunlight, you can capture the sunlight, you can combine with the photovoltaic system, or you can develop photo catalyst, and that can do your reaction, CO2 reduction. That's the process. Main thing is you can't do everything with the nature, so you have to go for the other process, for the industrially value added chemicals. That's the reason. Also, we are only using the carbon dioxide that is excess in the atmosphere. We are not depleting the carbon dioxide or not depleting oxygen, right? So we are only using carbon dioxide excess in the atmosphere. Hope that is clear. No, actually in laboratory scale, we have the 99% pure carbon dioxide available in the gas cylinder. And then first we, as a proof of concept, we have to use that carbon dioxide and we have to run our reaction. And our catalyst, if it really has a potential, then you can go for patenting and you can collaborate with the industry. And then there maybe they have facilities to collect the CO2 from the atmosphere, and then we can do. Already it is in process, like several countries, they are doing this. Fossil fuel. Yes. Can you repeat the question? Yeah, definitely. Like, because the main reason is the fossil fuels like coal or wood or something, or natural gas or everything is getting depleted, right? So after 20 years or 30 years or 15 years, we may not have access to these sources. So we have to go for alternate sources. And when you reduce carbon dioxide into CO, it is an industrially valued product, and it can be useful for other one. And also like ethanol can be used for gasoline, so it can be used as an alternative for the fossil fuel. So yeah, you're right. So it will be very helpful for getting. Okay. Okay. Yeah, actually, you mean the implementing what? I didn't get the question actually. Okay. Okay. Extracting. Yeah, true. So it is a good idea actually. But maybe in reality, you may face some challenges, like how efficient you are going to capture the CO2 using those towers, and how efficient you can store. There are two challenges. One is capturing carbon dioxide, and the other one is storing carbon dioxide. If you have efficient methods for capturing and storing, definitely it is possible. And like reality, it is always a challenge, right? Even if you see the electrical power grids, you are producing electrical energy in the power plants, but obviously when you are transporting or something through the power grids, obviously you have power losses, right? Same thing happens with the CO2 capture or CO2 reduction also. But people are trying in several countries. People are more caring more, because the NASA is now more concerned about the CO2 levels in the atmosphere, and the whole world is concerned about the CO2 emissions. So maybe in future, every country may develop or build their own CO2 capturing towers. In that case, we could capture more CO2 efficiently. And if we have efficient CO2 electrolyzers to convert carbon dioxide into value-added chemical, definitely there is a green future for sure. Thank you. Any other questions?
Okay, Arun Prakash sir, very kind of you, sir. Thanks and gratitude for your wonderful support towards the development of our students' career. On behalf of our management of AKCP, hereby I express my wholehearted thanks to you and your esteemed university for giving such a wonderful information about the sustainable production of value-added chemicals and fuels from carbon dioxide. So some seeds of intelligence in our students. Really, we had a wonderful presentation.
Thank you.
Dr. Arun Prakash Periasamy sir. Sir, whenever would like to plan in future, please let me know, sir.
Sure,
invite
sir.
our institution, sir.
Sure, sir. Thank you for your invitation, kind invitation, and thank you for this wonderful opportunity. It was nice delivering a talk.
Finally, one more request, sir. Kindly refer, sir. Let us know any of your friend, colleague who are able to guide and support for the development of our students' career. Kindly refer your friends, sir, for our future webinars. One more request.
Definitely, I will.
Friends or colleagues, your friends.